The minimum circuit amp rating is used only for wire sizing. The National Electrical Code, or NEC, addresses this in Article 430.52, which states the ampacity of the branch circuit conductors shall be at least 133% of the minimum circuit amperage rating specified on the equipment nameplate, or not less than the minimum branch circuit amperage rating specified on the equipment nameplate, whichever is greater. In this scenario, the minimum circuit amperage rating specified on the equipment nameplate is 52.1 amps. 133% of 52.1 amps is 68.9 amps. Therefore, the branch circuit conductors must have an ampacity of at least 68.9 amps. The maximum fuse or breaker rating is used to determine the maximum size of fuse or circuit breaker that can be used. The NEC addresses this in Article 430.53, which states the rating of a fuse or circuit breaker used to protect a branch circuit shall not exceed the maximum fuse or circuit breaker size specified on the equipment nameplate. In this scenario, the maximum fuse or circuit breaker size specified on the equipment nameplate is 60 amps. Therefore, the circuit breaker used to protect the branch circuit must not exceed 60 amps. The inspector was correct in failing the inspection because the 50 amp circuit breaker was too small for the alternating current system. The correct size circuit breaker would be 60 amps. Let's delve deeper into the NEC requirements to fully understand the rationale behind these rules. Firstly, let's break down Article 430.52 regarding the minimum circuit ampacity. The 133% rule is in place to account for the continuous operation of many alternating current systems. Continuous operation is defined as operating at maximum current for 3 hours or more. This sustained load can cause conductors to heat up, and dirtying the wire size ensures that the insulation doesn't break down over time, creating a fire hazard. Secondly, the NEC allows you to use the minimum branch circuit ampacity rating specified on the equipment nameplate, whichever is greater, but it's crucial to understand the implications. If the nameplate specifies a higher ampacity in the 133% calculation, it means the manufacturer has already factored in potential high inrush currents or other operational characteristics that necessitate a larger conductor. This takes precedence to ensure safe and reliable operation. Thirdly, consider the practical implications of undersized conductors. Overheating can lead to voltage drop, which reduces the efficiency of the alternating current system and can damage the motor over time. Undersized wiring also increases the risk of nuisance tripping of the circuit breaker, interrupting the operation of the air conditioning system. This creates inconvenience and potential safety hazards. Fourthly, let's examine Article 430.53 concerning the maximum fuse or circuit breaker size. The purpose of this requirement is to protect the motor and the branch circuit conductors from overcurrent conditions such as short circuits or ground faults. The maximum fuse or breaker size specified on the equipment nameplate is carefully determined by the manufacturer to provide adequate protection without causing nuisance tripping due to normal motor starting currents. Fifthly, it is important to differentiate between inverse time circuit breakers and fuses. Inverse time circuit breakers are designed to trip faster as the overcurrent increases, allowing for short duration inrush currents without tripping. Fuses, on the other hand, offer excellent short circuit protection due to their rapid response time. The NEC permits the use of either fuses or inverse time circuit breakers provided they meet the equipment nameplate requirements. Sixthly, consider the practical implications of using an oversized fuse or circuit breaker. While it may prevent nuisance tripping, it compromises the overcurrent protection of the motor and conductors. In the event of a fault, an oversized protective device may not trip quickly enough, allowing excessive current to flow, which can damage the motor, melt the conductors, and potentially cause a fire. Seventhly, it is important to note that the NEC permits the use of dual-element time-delay fuses in certain applications. These fuses are designed to withstand temporary overloads, such as motor starting currents, without opening. They provide both overload and short-circuit protection and can be a suitable option for alternating current systems with high inrush currents. Eighthly, let's consider the role of the electrical inspector. The inspector is responsible for ensuring that the electrical installation complies with the NEC and other applicable codes and standards. Their job is to verify that the conductors are properly sized, the overcurrent protection is adequate, and the equipment is installed according to the manufacturer's instructions. The inspector's decision to fail the installation was based on a clear violation of the NEC requirements for overcurrent protection. Ninthly, let's discuss some additional factors that may influence the selection of conductor size and overcurrent protection. These include the ambient temperature, the number of conductors in a raceway or cable, and the voltage drop. The NEC provides tables and guidelines for directing conductor ampacity based on these factors. It's crucial to consider these factors to ensure that the conductors can safely carry the load current without overheating. Tenthly, let's consider the importance of proper documentation. The electrical contractor should maintain accurate records of the conductor size, overcurrent protection, and other relevant information about the installation. This documentation can be helpful for future maintenance, troubleshooting, and inspections. It also demonstrates that the installation was performed in accordance with the NEC and other applicable codes and standards. Now, let's further elaborate on the specifics of Article 430 within the NEC as it pertains directly to motor circuits and their protection. This section is crucial for understanding the intricate details of motor installations, including those for air conditioning systems. Firstly, NEC Article 430 covers not just air conditioning motors, but all motors, and provides detailed requirements for motor circuit conductors, overcurrent protection, motor overload protection, and motor control circuits. Secondly, understanding motor starting currents is essential. Motors draw a significantly higher current when they start up compared to their running current. This inrush current can be several times higher than the motor's full load amps, or flow, and can last for a few seconds. The overcurrent protection must be sized to accommodate this inrush current without nuisance tripping, while still providing protection against sustained overloads and short circuits. Thirdly, motor overload protection is distinct from branch circuit overcurrent protection. Overload protection is designed to protect the motor itself from overheating due to prolonged overcurrent conditions, such as a locked rotor or excessive load. This protection is typically provided by thermal overload relays or electronic motor protection devices. Fourthly, the NEC specifies different methods for determining the size of motor branch circuit conductors based on the motor's full load amps and the type of motor. For example, conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current rating. Fifthly, the type of motor also affects the selection of overcurrent protection. Different motor designs, such as Design A, Design B, Design C, and Design D motors, have different starting current characteristics, which must be considered when selecting the appropriate fuse or circuit breaker. Sixthly, the NEC allows for the use of inverse time circuit breakers, fuses, or motor short circuit protectors, or MSEPs, for motor branch circuit overcurrent protection. MSEPs are specifically designed for motor circuits and provide superior short circuit protection compared to standard circuit breakers. Seventhly, the NEC also addresses the protection of motor control circuits. Control circuits are used to start, stop, and control the operation of motors. These circuits must be protected against overcurrent and short circuits to prevent damage to the control equipment and ensure safe operation. Eighthly, when dealing with multiple motors on a single branch circuit, the NEC provides specific rules for calculating the conductor size and overcurrent protection. The conductor ampacity must be sufficient to carry the combined full load currents of all the motors, plus any additional loads on the circuit. Ninthly, understanding the motor nameplate is critical. The nameplate provides essential information about the motor, including its full load amps, voltage, horsepower, service factor, and code letter. This information is necessary for selecting the proper conductor size, overcurrent protection, and overload protection. Tenthly, the NEC also covers the installation of motor disconnecting means. A disconnecting means is a switch or circuit breaker that can be used to energize the motor circuit for maintenance or repair. The disconnecting means must be readily accessible and capable of interrupting the motor's locked rotor current. Let's explore further the nuances of conductor ampacity and how various factors influence its determination, going beyond the basic rules and delving into practical considerations. Firstly, ambient temperature significantly affects conductor ampacity. The NEC provides ampacity correction factors for different ambient temperatures. When the ambient temperature is higher than the temperature rating of the conductor, the ampacity must be derated to prevent overheating. Secondly, the number of conductors in a raceway or cable also affects ampacity. When multiple current-carrying conductors are bundled together, the heat generated by each conductor can raise the overall temperature, requiring the ampacity to be derated. The NEC provides adjustment factors for different numbers of conductors in a raceway or cable. Thirdly, conductor insulation type plays a crucial role. Different insulation materials have different temperature ratings. Common insulation types include THHN, THWN, and XHHW. THHN and THWN have a maximum operating temperature of 194 degrees Fahrenheit, while XHHW has a higher temperature rating of 221 degrees Fahrenheit. Using a higher temperature rated insulation can allow for a higher ampacity in certain applications. Fourthly, the length of the conductor run can also impact conductor selection. Long conductor runs can result in voltage drop, which reduces the voltage available at the load. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, larger conductors may be required. Fifthly, the type of load also influences conductor selection. Continuous loads, such as lighting and heating, require conductors to be sized at 125% of the load current. Non-continuous loads, such as motors and appliances, may have different sizing requirements based on the NEC. Sixthly, conductor material matters. Copper conductors have a higher ampacity than aluminum conductors for the same size. Aluminum conductors are typically less expensive than copper conductors, but they require larger sizes to achieve the same ampacity. Seventhly, the NEC provides tables for determining conductor ampacity based on the conductor size, insulation type, and installation method. These tables are essential for selecting the appropriate conductor size for a given application. Eighthly, it is important to consider future load growth when selecting conductor sizes. Oversizing conductors slightly can provide capacity for future expansion without requiring costly rewiring. Ninthly, proper termination of conductors is crucial for ensuring safe and reliable connections. Conductors must be properly stripped, twisted, and terminated using approved connectors and tools. Loose or corroded connections can cause overheating and voltage drop. Tenthly, regular inspection and maintenance of conductors and connections are essential for preventing electrical problems. Over time, conductors can become damaged, corroded, or loose, requiring replacement or repair. Let's now discuss the intricacies of overcurrent protection devices, including fuses and circuit breakers, focusing on their selection, application, and coordination to ensure safe and reliable electrical systems. Firstly, fuses are single-use overcurrent protection devices that open the circuit when the current exceeds their rating. They are available in a variety of types, including time delay fuses, fast-acting fuses, and current-limiting fuses. Secondly, circuit breakers are reusable overcurrent protection devices that trip and open the circuit when the current exceeds their rating. They can be reset manually after tripping, unlike fuses which must be replaced. Thirdly, time delay fuses are designed to withstand temporary overloads, such as motor starting currents, without opening. They provide both overload and short circuit protection and are often used in motor circuits. Fourthly, fast-acting fuses are designed to open very quickly in response to a short circuit. They provide excellent short circuit protection, but may be susceptible to nuisance tripping due to temporary overloads. Fifthly, current-limiting fuses are designed to limit the magnitude of the fault current during a short circuit. They provide superior short-circuit protection and can help protect downstream equipment from damage. Sixthly, circuit breakers are available in a variety of types, including thermal magnetic circuit breakers, electronic trip circuit breakers, and instantaneous trip circuit breakers. Seventhly, thermal-magnetic circuit breakers use a combination of thermal and magnetic elements to provide overcurrent protection. The thermal element responds to overloads, while the magnetic element responds to short circuits. Eighthly, electronic trip circuit breakers use electronic sensors and microprocessors to detect overcurrent conditions. They offer greater accuracy and flexibility compared to thermal-magnetic circuit breakers and can be programmed with different trip curves. Ninthly, instantaneous trip circuit breakers, also known as motor circuit protectors, or MCPs, are designed to trip very quickly in response to a short circuit. They are often used in motor circuits to provide fast short circuit protection. Tenthly, the selection of the appropriate overcurrent protection device depends on the specific application and the characteristics of the load. Factors to consider include the load current, the interrupting rating, the voltage rating, and the coordination with other protective devices. Let's delve into the critical area of selective coordination of overcurrent protection devices, a vital aspect of electrical system design that ensures safety, reliability, and minimizes downtime. Firstly, selective coordination is the process of selecting and coordinating overcurrent protection devices so that only the device closest to the fault opens, minimizing the impact on the rest of the electrical system. Secondly, proper selective coordination prevents upstream overcurrent devices from tripping unnecessarily during a fault, which can cause widespread power outages and disrupt critical operations. Thirdly, achieving selective coordination requires careful consideration of the time current characteristics of the overcurrent protection devices. The time current characteristic is a graph that shows the amount of time it takes for a device to trip at different levels of overcurrent. Fourthly, to achieve selective coordination, the time current curves of the overcurrent protection devices must be coordinated so that the downstream device trips before the upstream device for all levels of overcurrent. Fifthly, the interrupting rating of an overcurrent protection device is the maximum amount of fault current that the device can safely interrupt without failing. The interrupting rating must be sufficient to handle the available fault current at the point of installation. Sixthly, the voltage rating of an overcurrent protection device must be equal to or greater than the system voltage. Using an overcurrent protection device with an inadequate voltage rating can result in failure and pose a safety hazard. Seventhly, the NEC requires selective coordination for overcurrent protection devices in certain critical applications such as hospitals, data centers, and emergency systems. Eighthly, achieving selective coordination can be challenging in complex electrical systems with multiple levels of overcurrent protection devices. Computer software and coordination studies can be used to analyze the system and select appropriate devices. Ninthly, regular testing and maintenance of overcurrent protection devices are essential for ensuring that they function properly and maintain selective coordination. Over time, devices can degrade or become damaged, requiring replacement or recalibration. Tenthly, proper documentation of the selective coordination study and the overcurrent protection device settings is crucial for future maintenance and troubleshooting. The documentation should be readily available and updated whenever changes are made to the electrical system. We will now discuss the importance of proper grounding and bonding in electrical systems, highlighting the safety benefits and code requirements that ensure personnel safety and equipment protection. Firstly, grounding is the intentional connection of a neutral conductor or equipment enclosure to earth. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and clear the fault. Secondly, bonding is the connection of all metal parts of an electrical system to create an electrically conductive path. Bonding ensures that all metal parts are at the same potential, minimizing the risk of electric shock. Thirdly, the grounding electrode system is the means by which the electrical system is connected to earth. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. Fourthly, the equipment grounding conductor, or EG, is the conductor that connects the metal parts of an electrical system to the grounding electrode system. The EGC provides a low impedance path for fault current to flow back to the source. Fifthly, the neutral conductor is the conductor that carries the unbalanced current back to the source in a single-phase electrical system. The neutral conductor is typically grounded at the service entrance. Sixthly, the NEC requires that all metal parts of an electrical system that are likely to become energized be grounded or bonded. This includes equipment enclosures, metal conduit, and metal water pipes. Seventhly, proper grounding and bonding can prevent electric shock, reduce the risk of fire, and protect equipment from damage. Eighthly, grounding and bonding are especially important in wet or damp locations where the risk of electric shock is higher. Ninthly, the NEC provides detailed requirements for grounding and bonding, including the size of the grounding electrode conductor, the size of the equipment grounding conductor, and the methods for connecting grounding and bonding conductors. Tenthly, regular inspection and testing of grounding and bonding systems are essential for ensuring that they are functioning properly. Grounding and bonding conductors can become corroded or damaged over time, requiring replacement or repair.